I am here today to convince you that it is okay to get a value of 0 from higher order integrals like double integrals, triple integrals, etc. To do this video, I paused my rewatch of the Star Trek episode Amok Time right in the middle when it was starting to get good. So I hope you appreciate the sacrifice that I am making. This story came to mind again because of chatter around a problem on one of the math subreddits on Reddit. I actually did a video about it a couple of days ago, so if you want, you can go find it. But it was a context of a contour integral, and the poster said, hey, I don't think I did this right because I was getting 0. And that happens a lot. You know, I taught for 24 years, and it was pretty common, especially, you know, in Calc 3 multivariable calculus, for students to come and say, oh man, I tried this a couple of times. It's a triple integral, but I keep getting 0 and I don't know why. And the fact is, it's okay to get 0 for double integrals, triple integrals, and all of that. So I just want to convince you of this and actually help you make predictions about when that event might happen. Okay, so don't fall into that trap of panic when you're doing a multivariable integral and you get 0 as an answer. It could be fine. Okay. In fact, you already know plenty of cases where getting 0 for the value of an integral is fine. One of the first big, ooh, that's cool moments in Calc 1 comes from the definite integral of sine of x, usually on 0 to 2 pi. So you're learning how to do definite integrals. This one gets thrown at you. You find the antiderivative of sine, you plug in 0 and 2 pi and subtract, and you get 0. Okay, whatever. But then you match that up to the picture of the graph of sine of x on 0 to 2 pi, and it's like, ooh, that's pretty cool. Because remember, what you're doing by integrating sine of x from 0 to 2 pi is you're finding the net area, quote unquote, under the curve, which in this sense, in this setting, the area under the curve actually is a pocket that's above the curve, but this is signed area. That's S-I-G-N-E-D, okay, because the area from this pocket above the x-axis has a positive value. The area that we calculate below the x-axis is assigned a negative value, and since the shapes are exactly the same, the total net area ends up being 0. And it's not just assigned, right? It's not something we made up. You have to go back to the original Riemann sum definition of an integral when you're doing all your f of x delta x's, right? So when we're in between 0 and pi, all of our f of x's are positive values. When we're in between pi and 2 pi, all of our f of x's are negative values. And so we build those summations and run the limit, et cetera, et cetera. This area between pi and 2 pi generates a negative contribution to the overall integral, which becomes 0 because of this nice symmetric balance from the two pockets. Okay, and then you go off to the races from there, because then you can go to the cosine graph, and integral from 0 to pi of that is 0, and you draw the graph and you see exactly why. And you know, maybe you take the sine function and let it wiggle way out and think of an integral like that. You already know it's probably going to be 0 depending on the endpoints. And it doesn't even have to involve trig functions. Surely you know by now that if you integrate any odd function like x cubed from negative something to positive of that same thing, you're going to get 0 because of the above and below the axis symmetry of the graph in perfectly matched but opposite pockets, right? So all these cases, you get 0 as the value of an integral, and it doesn't bug you, and in fact it's pretty cool when that happens. But then we get to multivariable calculus, and now it's for most people, you've had this semester in between, right, where you're doing all this nonsense in Calc 2, but Calc 3 is more a direct follow-up of Calc 1 than it is of Calc 2, right? But it's been over a semester now, and now you're doing integration again. And it's in more complicated geometries. The calculations are longer. So you go through all this work and you get 0. And then you panic because, am I calculating a volume? How can a volume be 0? Or I'm calculating an area. How can an area be 0? Okay, so I must have done something wrong. And the answer is no, you might not have done anything wrong. So let's start thinking about what we're calculating with double integrals. As an example, double integral of the function 3x squared y over some region in the xy plane, right? Just like a single integral is calculating area under a curve, this double integral is calculating the volume under the surface f of xy equals 3x squared y. And under, I'm emphasizing with the stupid rabbit ears, because if the value of the function is positive and this surface is above the xy plane, then that value comes back as a positive number. But if that surface goes below the xy plane, the value that you're calculating for that contribution to the overall volume comes back as negative, just like in the single variable case, okay? And so getting a total cancellation out to 0 is just fine, just like it was back in Calc 1. As you're thinking through these problems, it might be a little bit more advantageous to think of one of these integrals in a loose sense as you're accumulating values of this function that you're integrating. So you're the little calculus ant, and you are walking around in the xy plane throughout the domain of integration that you've been given, and you have your bucket, and at every point in this domain you get the value of the function and you throw it in your bucket, and some of the values are positive and some of them are negative. How is it all going to wash out in the end? Okay, so we can do some predictions before we even do any calculations. So double integral of 3x squared y over a rectangular region where x goes from -3 to 2, y goes from -2 up to 2. So here is a very badly drawn version of that region. And let's say we pick this point up here. We get its contribution to 3x squared y. Now, since x is squared, it doesn't matter where we are on the x-axis, that contribution is always positive. But y can contribute a positive or a negative value, depending on where we are. So we get 3x squared y from this point that I've already circled. And let's say that, whatever value that y coordinate is, we go down here to the exact opposite. The contribution to 3x squared y from that point is going to be the opposite of 3x squared y from the above point. So the net from these 2 points is 0. They cancel each other out. And maybe we go over here. Here's another pair where the contribution from one will exactly cancel the contribution from the other because we've got an exact positive-negative match with the y coordinate. So for every x coordinate that we go through, every positive y has an exactly matching negative y. So all in all, we would expect the net contribution to 3x squared y from all of the points in this region to end up balancing out to 0. Okay? So in that case, setting that integral up, putting on the limits, running all the calculations, and getting a result of 0, that's not bad. That's actually good and expected. Now here's a slightly different case where I've just stretched the y range, domain, whatever you want to call it, a little bit. Next slide, please. There we go. Again, badly drawn. The top isn't quite flat, but we're all friends here, so we'll pretend that it is. So here are the 4 points that, I don't want to keep using red. Here are the 4 points from the previous example that their contributions to 3x squared y, the positives canceled out the negatives. And that total net cancellation, because here this bottom boundary goes down to -2, that net cancellation will help all the way up to +2. So every contribution to that integral from this box, which was the previous problem, is 0. But there's this extra band up here, say at y equals 2.5, where that contribution to 3x squared y does not have a counterpart down there in the domain of integration to balance it out. And so for this integral, we would not expect an answer of 0. For this third one, x is going from 0 to pi over 2. Now I took all the negatives away from x. Is that going to affect anything? And the answer is no, because again, x is being squared. So x doesn't have any role in the positive versus negative cancellation. It's all about the y's. And since here the span of y is symmetric, every positive contribution does have a negative counterpart. All in all, 0. And these regions don't even have to be square. Inside the unit circle, every point, did I draw a unit circle? No, I didn't. I'm going to draw a unit circle. Ta-da! Put some axes in there. Okay, so again, 3x squared y within the unit circle. So these are 1s and -1s around the perimeter. Pick a point there. It contributes to 3x squared y. Well, guess what? Here's the matching counterpart at exactly the -y that will counteract the 3x squared y from the first point. And that point up there is exactly counteracted by this point down here. This point right here is exactly counteracted by that point there. So everywhere in this circle, everything is exactly counterbalanced by something else. And so, yeah, we would expect this result to be 0 as well. And just so you trust me, here is some maple with these integrals already set up. So the first one we predicted 0. The second one we predicted non-zero. The third one we predicted 0. And the fourth one we predicted 0. Nope, hit return the right way. That helps. There we go. Down there at the bottom of the screen. So 3 of those 4 ended up being 0, just as predicted. Good stuff. Now, the same thought process can go on for triple integrals. It's a little bit more difficult to visualize, but you can do it. So when we do a triple integral of f of x, y, z dv, we are not calculating a volume, right? Double integrals, their volumes under a function or under a surface, which could be positive from above the xy plane, negative from below the xy plane, right? Triple integrals, unless we're integrating one specific function, we're not calculating volume anymore. I don't even know what we're calculating, right? It would be a 4-dimensional quantity. So for triple integrals in particular, flush out of your mind the idea of, oh no, I got 0, that has to be bad. Okay, because we are, except in a rare case, when you're specifically asked to calculate a volume and you set it up the proper way. Otherwise, getting 0 is just fine. And we can predict, okay, whether or not we might get 0 for some simple cases like this one. So we're going to think about the triple integral of the function xyz squared over a rectangular box where x goes from -1 to 1, y goes from -2 to 2, and z goes from -5 to 5. Now notice the z is squared, so that's a wash. It doesn't matter where we are in the z. Those contributions are all positive, but x and y can go either way. And notice, just like in the 2D case, when we think about the contribution to x in xyz squared, every value of x that we use will have a counterpoint that will contribute exactly the opposite, and same thing for y. So when it's all said and done, as the calculus ant is walking around this 3-dimensional box and putting values of x, y, z squared into that ant's little bucket, every positive contribution has a matching negative counterpart. The net result will be 0. F of x equals x, y, z, and we're now over 2 concentric spheres of radius 2 and 4. Okay, I'm gonna regret this, but let's give it a shot. There's the sphere of, there's the origin, radius of 2. Okay, it's not terrible so far, but here it's going to get pretty awful. So here's the bigger sphere. Has a radius of 4, so this thing's coming out like that, coming out and around like that. Okay, that's gross. But, the idea is, here we are, we're in this 3-dimensional volume E in between a sphere of radius 2 and a sphere of radius 4. And we are accumulating values of x, y, z, just to keep it simple. Just like in the other cases, every point that we pick, like right there, let's say that's over here and, it's over the plane, the XY plane right there. So x and y are what they are, but down here, there's going to be a matching point with the negative z value. So whatever contribution this point gave, the exact opposite is coming from that point to the function x, y, z. And no matter where we go, positive, negative, every contribution to x, y, z has a balancing counterpart. So we would expect this triple integral of x, y, z in between two concentric spheres to end up being 0. And problems like this are why I'm doing this in the first place, because it's a lot of work to do that integral, because you're probably not going to set it up in rectangular coordinates. You're probably going to set it up in spherical coordinates. So x, y, z in spherical coordinates, that's going to be grotesque. And then on top of that, your dv opens up into rho squared sine phi d rho d phi d theta. That's gross. Put all that stuff together, slap on some limit. Now the limits are going to be nice because they're all going to be constants, right, in spherical coordinates. But still, it's a lot of work and a lot of grunt work to get through the calculation. And then you end up getting 0. Don't be like, oh no, I did all that work and I got 0. It's actually good that you got 0 because you could have predicted that you were going to get 0. Triple integral of x squared plus y squared plus z squared over this region E, which is the upper half of the unit sphere. Not going to give us 0. In fact, as soon as I saw f of x, y, z equals x squared plus y squared plus z squared, every value of that function is positive no matter where we are, no matter what the x, y, and z coordinates are. So pick a point, its contribution to the function is positive. There is no counterpoint that will contribute the negative to balance that out because everything is squared. So the first two examples I would expect 0, the last one I would not. Okay, and again, back to this idea of, when are we actually calculating areas and volumes, right? A double integral of the function 1 is actually calculating for you the area of the region of integration, as long as you can take this given region and describe it using bounds on the integrals. If you integrate the function 1, you've calculated the area of that domain. So we would not expect zeros for something like this. A triple integral of a function, specifically 1, does give us the volume of this three-dimensional region. And in fact, that's a very standard problem. Use a triple integral to calculate the volume in between this upwards paraboloid and this downwards cone or something like that. So you can calculate the volumes of some pretty interesting regions, but to do that, you're integrating the function 1. Okay. If I have a triple integral of anything else besides 1, I am no longer calculating a volume, and so getting 0 is okay. And the in-between case, a double integral of f of x, y, is calculating the volume under that surface, but it's a signed volume. Surface above the xy plane positive, surface below the xy plane contributes negative. It can balance out to be 0, just like that integral from 0 to 2 pi of sine of x case that kicked this whole thing off. So the main moral of this whole story is don't fall into that trap of, oh no, I did all this work for a double integral or a triple integral and I got 0. What did I screw up? Maybe you did everything exactly right. And in fact, in simpler cases, you should be able to predict going into the integral whether you're going to get 0 or not before you even run the numbers, right? If you can do that, it's awesome. It'll ease your mind quite a bit. So that's the story. I might return and do another version of this, thinking about contour integrals. Surface integrals are a little bit hairier, especially in the vector versions, but at least the scalar version of a surface integral, we could do it. So I'll probably follow up with a second video like this in those more interesting cases. But for now, thanks for watching, and don't be afraid of getting 0 for those double and triple integrals.